This is a pre-calculus lesson on the special right triangles and describing angles in the radian unit measure. Pause the video here and try the warm-up on page 5. So the first thing we have to do is find this missing leg of the right triangle. I'll call it Q because it's opposite angle Q. So, oh no, I don't like that because of the 9. Hang on, I'm just going to make it an x. All right, 9 squared plus x squared equals 15 squared. 81 plus x squared equals, well, 15 squared is 10 plus 5 times 10 plus 5. We'll use the area model. That's 100. 5 times 10 is 50. 10 times 5 is 50. 5 times 5 is 25. So when I add all of those up here, that's 100 plus 100 plus 25 for a grand total of 225. Subtract 81. Square root. And x is 12. So this side length is 12. And the question now is, write the 6 trig ratios for Q and H. I'm not going to have enough room here. All right, let me bring my triangle down. All right, so I'm going to start sine of Q, cosine of Q, tangent of Q. The reciprocal of sine is cosecant. The reciprocal of cosine is secant. The reciprocal of tangent is cotangent. And so here's the sine, here's angle Q. So 12 is opposite, 9 is adjacent, and 15 is the hypotenuse. So sine is 12 over 15, cosine is 9 over 15, and tangent is 12 over 9. All the reciprocals. And now let's repeat that for angle H. Did it say H? Q and H. Okay, now we got to repeat that for H. Sine of H, cosine of H, tangent of H, cosecant of H, secant of H, and cotangent of H. Okay, so now, if this is our angle, 9 is the opposite, 12 is the adjacent, and 15 is still the hypotenuse. So sine is 9 over 15, cosine is 12 over 15. Tangent is opposite 9 over 12. And all the reciprocals done. So now on the next page, on page 6, we're going to develop the special right triangles. And these special right triangles we are going to use so often, almost every day between now and third quarter. We're going to use them so often, they're going to show up in your dreams. You're not going to be able to stop thinking about these triangles. We're going to develop the special right triangles from these two regular polygons. We have a regular triangle, which means equal sides, equal angles. All the angles in a triangle add up to 180. There's 3 of them, so each angle is 60 degrees. And then just for simplicity's sake, I'm going to call each side length 2. Now I'm picking that on purpose. It's going to help us get where we're going. It's going to make things a lot nicer as we start drawing more things on this triangle. So I'm going to decide each side length is 2. Where the special part comes in is when I draw the height, which is this perpendicular, that bisects this top angle to be 30 degrees. And that bisects this side where each part is 1. And the special right triangle we're going to use is a 30, 60, 90 triangle from here. This is half of this triangle. And I would like you, with the Pythagorean theorem, to find this segment. So we're going to focus on just this yellow triangle here. So y squared plus 1 squared equals 2 squared. So we got y squared is 3, square root, square root. That segment is the square root of 3. And this segment right here is the square root of 3. So this special right triangle across from 30 is a side length of 1. So if I'm going to draw just the special triangle we're going to use, we've got a 30. That's better. We've got a 30, 60, 90 triangle. Across from 30 degrees is a side length of 1. Across from 90 degrees is a side length of 2. And across from 60 is a side length of root 3. So let's do that all again with the square. We know in a square that all the angles are 90. And this time, instead of doing a perpendicular, which would just make 2 rectangles, I want to draw the diagonal. And this diagonal bisects these angles. So half of 90 gives me 45 degrees. And since I didn't cut any of the side lengths in half, I'm going to call the square all side length 1. So now using Pythagorean theorem, find the hypotenuse. So the square root of 2 is h. So we have a 30, 60, 90 special right triangle and a 45, 45, 90 special right triangle, where across from each 45 is 1 and the hypotenuse is root 2. These are the 2 triangles we are going to use over and over and over and over and over and over and over again. So 30, 60, 90, I would put this one on a note card, and 45, 45, 90, I would put this one on a note card. Example, using the triangle to the right. We have a 60 degrees in the bottom corner, which means this top piece has to be 30. So using the special right triangle, I want you to label the side lengths on the bottom of the orange here, the perpendicular, and the hypotenuse. Across from 30 is 1, across from 90 is 2, across from 60 is root 3. So now when we do sine of 60, that's opposite over hypotenuse. Cosine of 60 is adjacent over hypotenuse. Tangent of 60 is opposite over adjacent. And all the reciprocals and then we have to fix up the ones with the square root in the denominator. We have to make them look nicer where there is no square root in the denominator. So I'm going to multiply by a value of 1. Root 3 divided by root 3 is 1. And I'm choosing root 3 because now my denominator, root 3 times itself, is the square root of 9. The square root of 9 is just 3. And my numerator is 2 root 3. So cosecant of 60, the best answer is 2 root 3 over 3. I'm going to do the same thing for cotangent. And we get 1 root 3 over 3. Now we have a 30-degree angle down here, which means 60 is up here. Labeling our special right triangle side lengths, across from 30 is 1, across from 90 is 2, across from 60 is root 3. So now for 30 degrees, sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. All the reciprocals. And then anything I need to fix, we're going to rationalize this denominator, meaning no square root in the denominator. And then this one. All right, now we've got 45 degrees. So on page 7, pause the video and look back at the special 45, 45, 90 triangle and label those side lengths. There's going to be 1, 1, root 2. For the 45, it doesn't matter whether you look at the top one or the bottom one. It's isosceles, so it's going to be the same. So sine of 45 is opposite over hypotenuse. Cosine of 45 is adjacent over hypotenuse. Tangent is opposite over adjacent. I will fix those in a minute. All the reciprocals. And our fixing. So 1 divided by 1 is just 1. And now that square root of 2 is in the denominator, we're going to multiply by root 2 over root 2. Because root 2 times itself is just 2. 1 times root 2 is root 2. These are the same, so I'm just going to jump straight to root 2 over 2 because I know it's going to match that one. Much, much more with these special right triangles coming every single day after now. The second part of our lesson today is about radian measurement. When we measure angles, pretty exclusively up till now, we've used degrees. Depending on what Algebra 2 class you had last year, you did, some of you might have talked about radians, but that's last year, so let's start from scratch. A radian is a measurement of an angle, and it's the ratio, which is the division, of the arc length, which is part of the circumference, to the radius. So I have a visual for you here. The unit of 1 radian is when I take the radius and I lay that around the circumference of the circle. So here's an animation. So that's 1 radian. So going between radians and degrees, I can see I have 1 radian, 2 radians, 3, and a little bit more. So halfway around the circle is pi radians. 180 degrees equal to pi radians is going to be a fact that we use over and over and over again. I'll play that animation one more time so you can see how there's 3.14 radians in 180 degrees. So the entire circle is 360 degrees. So if we look at a circle, if I take a ray, my radius, and I swing it all the way around, it goes around 360 degrees. The ratio of the circumference, which is 2 pi r, divided by the radius, so ratio, the whole circumference divided by the radius, simplifies to 2 pi. So 360 degrees equals 2 pi radians, which is why 180 degrees equals pi radians. I could divide both by 2 and get the same conversion of 180 degrees equals pi radians. So let's convert the following to radians and degrees. I'm going to use a proportion every time. 315 degrees, so my proportion to radians is going to be pi is to 180 degrees as some amount of radians is to 315 degrees. So if I compare radians over degrees to radians over degrees, I can solve for this variable x. So to do that, I'm going to multiply both sides by 315. And we get 315 pi over 180. We have to reduce that. 315 and 180, they both end in that 5 and 0, so those divide by 5. So let's see. If I reduce by 5, 5 goes into 31 6 times. 5 goes into 15 3, so that's 63 pi. And then 5 goes into 180. Oops. 5 goes into 18 3 times. 5 goes into 5 goes into 36, so that's 63 over 36. And then another neat little trick, 6 plus 3 is 9. 3 plus 6 is 9. So both of these values divide by 3. If you add up the digits and it's a multiple of 3, like 9, 12, or 15, that number divides by 3. So that's 21 pi. And then 36 divided by 3, that's 12. Oh, 21 and 12, those divide by 3. And we finally get to our answer, whew, that was a lot of work, of 7 pi over 4. So 7 pi over 4 radians equals 315 degrees. That was a complicated one to start with. Okay, let's do it again for 270. I have pi radians to 180 degrees equals some amount of radians to 270 degrees. I'm going to multiply both sides by 270. So we get 270 pi over 180. Well, I can divide both of these by 10 to get 27 pi over 18. Oh, 27 and 18, those divide by 3. 9 pi over 6. 9 and 6, those divide by 3. And we get 3 pi over 2. So now we got to go the other way. I can set up a proportion again. I can say that, I just need more room. So we're going to say pi is to 180 degrees as pi over 6 is to a missing amount of degrees. So now my degrees is missing. And to solve this, I can multiply both sides by x. So now I've got x times pi over 180 equals pi over 6. And then on this side, I want to get the x by itself, so I'm going to multiply by 180 over pi. So 180 divides to 1, pi divides to 1, so I'm left with x. And on this side, that's 180 pi over 6 pi. The pi's divide. They go away. It equals, that simplifies to 1. So I'm left with 180 over 6, which 180 and 6 can both divide by 3. Let's divide these by 3 and go to 60 over 2, which is 30. So this is 30 degrees. Now there's a little bit of an easier way. That was kind of complicated. An easier way is to make a straight replacement. I can replace pi radians with 180 degrees. They're equivalent. And look, we got the same thing right here. So I'm going to do this one the easier way. I'm going to replace the pi with 180 degrees. I don't want to multiply 4 times 180. I'm going to reduce the 180 and 3 again. So 180 and 3, those both can divide by 3. We're left with 60 here. And now 4 times 60 is 240 degrees. If you wanted to set up a proportion, you could do that. It's totally fine. You could work through the same thing and get the same answer. So for our last part on page 8, we are going to draw some angles in radians. An important part of drawing angles, and we're going to get into this on our next lesson, is the initial ray is over here on the positive x-axis. And we're going to rotate counterclockwise. So our theta is going to rotate counterclockwise. This is the Greek letter theta. So let's estimate where pi over 2 radians would be. From when we looked at that animation, we knew that a half a circle is pi radians. That's 180 degrees. So this is pi cut in half. So if I rotate this halfway, this angle here is pi over 2. That's 90 degrees. 180 divided by 2 is 90. We're going to have to get used to radians. In the beginning, we can convert. It's okay to think of this as 180 divided by 2 and think in 90 degrees. But eventually, you will have to think in radians, because if you're converting every single time, you're just going to run out of time. It's not efficient. So this is saying take half a circle, pi radians, into thirds. So if I can try to cut this into thirds, that's pretty good. Here would be pi over 3 radians. If I want to think of this in terms of degrees, that is 60 degrees. All right, 2 more. Pi over 4 says take this half a circle and cut it into fourths. So here was our pi over 2. So I'm going to cut that in half. No, let's see, I can do better than that. And this amount would be pi over 4. I can cut another piece over here. So we got pi over 4, pi over 4, pi over 4, pi over 4. So that's half a circle cut into fourths. That's 45 degrees. Now cutting into sixths. So I've got pi. I guess I could take my thirds. I'm going to draw it in thirds again. Let's try again. So if I cut this semicircle into thirds and then cut each of them again in half, there we go. This would be pi over 6 radians, which is 30 degrees. Okay, so your homework now is page 9. You're going to convert. If you're, as a quick summary, if you're given radians, replace pi with 180 degrees and simplify. That's usually the fastest way. If you're given degrees, make a proportion and solve. So the proportion is going to be pi radians to 180 degrees is some missing radians to the amount of degrees you're given. Some of these we've already done, and you can jump right to how many radians that would be if you remember or you look back at those prior pages. Don't forget to check your answers in Drive.